Good day and welcome to the February Pacific Northwest Drought Early Warning System Drought and Climate Outlook webinar. My name is Britt Parker and I am with the National Integrated Drought Information System at NOAA. This bi-monthly webinar series hosted by NIDIS, the USDA Northwest Climate Hub, and the Oregon Climate Change Research Institute is designed to provide partners and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect recent, current, and forecasted conditions and climatic events, but also include discussions of observed impacts and other relevant updates across the region. Webinars and recordings and other supporting materials will be posted on drought.gov later this week. Note that after today's webinar, you will have the opportunity to provide feedback that will help us improve this webinar series. So please take a moment and tell us what you think. Today's speakers include Nick Seiler with the Oregon Climate Service and Oregon State University to talk about the climate recap and current conditions. We have Aaron Peters with NOAA's National Weather Service Western Region to give us seasonal conditions and the climate outlook. Then we are hearing two presentations on snowpack and snow drought. The first from Ben Roberts Perel, formerly of Oregon State University, on some work he did while at Oregon State on snow drought in the Pacific Northwest, the role of choosing and processing data. And finally, we'll hear from David Foster Hill, also of Oregon State University, on filling the gaps, crowdsourcing snow information, and a new way to think about snow storage. Before we begin the presentations, we want to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops science-based, region-specific information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. Visit the website in the chat box to get more information. The Oregon Climate Change Research Institute is a network of dozens of researchers at Oregon's public universities that work closely with one another, work closely with other public and private entities. OCRI is housed at Oregon State University. It advances understanding of regional climate impacts and adaptation. OCRI also hosts the Oregon Climate Service, the Office of the State Climatologist of Oregon. Again, there'll be more information with links in the chat box. NIDIS was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought risks by providing those affected with the best available information and resources to assess the potential for drought and to prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners and stakeholders share information and actions to help communities cope with drought. While the ultimate goal is a national early warning system, we recognize that impacts and early warning information differ across regions. Each DEWS has many of the same base ingredients, but ultimately have their own flavor to reflect the needs of the regions. And you can find more information on NIDIS and the Pacific Northwest DEWS at drought.gov, and those links will be in the chat box as well. Just a couple more highlights before we move into the presentations. To facilitate our early warning system, more precipitation observations are needed. We encourage you to join CoCoRaHS, the Community Collaborative Rain, Hail, and Snow Network. This is a unique nonprofit community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, as well as condition reporting. Observations by CoCoRaHS observers of precipitation events or the lack thereof are important to capture and improve our understanding of weather. To become a volunteer or learn more, visit cocorahs.org. Over the past 10 years, the climate hubs have built trust by working across the U.S. Department of Agriculture and with partners to support climate-informed decisions for robust agriculture, healthy forests, and resilient communities. The Pacific Northwest DEWS looks forward to continuing to partner with the Northwest Climate Hub in supporting drought preparedness. You can read more about their accomplishments at the link in the chat box, and we just want to say congratulations on their 10-year anniversary. This is an exciting time for the Office of the Washington State Climatologist. They just released a strategic plan to guide the next 5 years of their work, and now they're celebrating the retirement of Dr. Nick Bond and beginning their search for a new state climatologist. They're looking for someone to direct the activities of the office, advance the priorities of their strategic plan, and lead fundraising efforts to grow their capacity. For links to the strategic plan and to the job announcement, please see the link shared in the chat box. And finally, there are new ways to stay in touch with NIDIS. In the past, if you registered for our webinar, we were able to add you to our email list so that you would get the recording. This is no longer the case. So if you came upon this webinar in any other way than a direct email to you and you want to receive the recording and other pertinent information for the Pacific Northwest DEWS, please follow the link in the chat box and sign up. You may also be interested in our bi-weekly Dry Times newsletter and our tribal engagement newsletter if you're associated with or work with tribal nations. And with that, I'm going to turn our presentation over to Nick Seiler to hear about the climate recap and current conditions. Let's see. Okay, Nick, it should be coming to you.
Sorry.
No, you're good.
I accidentally shared my webcam, which is not what I want to do. Stop sharing my webcam. Can you see my screen now?
Yes, we can, and just
sorry
yeah.
about that.
No, don't worry.
Okay. Good morning and good afternoon, everyone. Thanks, Britt, for the introduction. My name is Nick Seiler. I'm an assistant professor of atmospheric science at Oregon State, and I'm also the associate state climatologist for Oregon. So I'll be giving the update. And for my background image here, I've chosen this image that was posted to the Instagram account for the Teton Pass ski area in western Montana on February 1st, explaining their decision to close their ski area for the remainder of the season due to lack of snow. So we'll be talking a bit later about how much of this region, Western Oregon and North Idaho, are actually seeing record low snowpack conditions right now. Okay, so here's the overall drought conditions according to the U.S. Drought Monitor for the Pacific Northwest region. And you can see that about 20% of the region is in either D1 or D2, so moderate drought or above. Much of the D2 drought, all of the D2 drought is in North Idaho or Western Montana. Western Oregon and Western Washington look pretty good by comparison. This map shows the current drought conditions that I just showed on the previous slide on the bottom, and then we're comparing that on the top to the drought conditions on December 12th, which is just prior to the last update in December. And overall, conditions look pretty similar, but we do see that conditions have improved a bit in Western Oregon and Western Washington, primarily due to a series of storms that impacted the region in early January. And we've seen some deterioration in Western Montana and North Idaho as well. These were regions that didn't have any D3 drought in December, and we've started to see some D3 drought pop up. This map shows the water year precipitation as a percent of the median. Water year is defined as October 1st, so this is the accumulated precipitation since October 1st as a percent of average. And you can see that in the southern part of the region, conditions are pretty close to average. In much of the upper Snake Basin, they're significantly above average. But we see pretty significant deficits in the northern part of the domain. That includes virtually all of the Washington Cascades, but especially, again, North Idaho and Western Montana, where precipitation has been around 70% of normal. This map shows the same information, but by watershed, also as a percent of median. And this data is based on high elevation snow-till stations. So this is just sampling the higher elevation stations. But similar to the last map, we see conditions or precipitation pretty close to average in the southern part of the domain, hovering right around 100%. But when we move up into Washington, North Idaho, and Western Montana, we see precipitation since October 1st significantly below average, even below 70% of average in parts of North Idaho and Western Montana. This map shows the same information, but for snowpacks. This is snow water equivalent. And again, in the southern part of the domain, conditions are pretty close to average. But when we look at the northern part of the domain, the deficits in snowpack are even larger than the deficits in precipitation as a percent of average. So I'll just toggle back and forth here. And we can see that, in much of Washington, where precipitation is 80% of average, snowpack is 50 to 60% of average. And the same is true in much of North Idaho and Western Montana. When we look at the same data, but by specific snow-till sites, we see that the station level precipitation data are broadly consistent with the basin scale results that we just saw, pretty close to average, even a bit above average in much of Oregon and southern Idaho, significantly below average in Washington, and especially in North Idaho and Western Montana. The station level snowpack data, though, is a bit more interesting. And here we see, I think, a pretty significant elevation signature, especially in the Cascades of Washington and Oregon. If we look at sites here that are pretty close to the crest of the Cascades, snowpack at those sites tend to be closer to average, but if you look just a bit west of the crest, we see much larger deficits. So just as an example of that, here I've shown snowpack and precipitation data for a site near the crest of the Oregon Cascades at a place called Hog Pass. This is near Santiam Pass. The red line here shows median snow water equivalent. So this is the average over 30 years at this site. And the x-axis here is time, so beginning at the beginning of the water year on October 1st. And then the gray line here is the median precipitation. The blue line shows snow water equivalent for this year. And you can see that we were running way below average up to the beginning of the calendar year, and then a series of storms in early January brought our snowpack at this site pretty close to average, and we've hovered around average in both snowpack and in precipitation ever since. So this is a site that's at almost 5,000 feet, right at the crest of the Cascades. And then we can contrast that with a site just a bit west of this location that's at lower elevation, 3,500 feet. And this site also saw a pretty big increase in snowpack in early January, bringing it pretty close to average. But then there was this period of pretty rapid melt beginning right after the cold spell around Martin Luther King weekend, leading to almost complete melt out at this site by the beginning of February. So we saw rapid melt at some of these lower elevation sites, and less melt at the higher elevation sites near the crest. And the reason for that rapid melt in the last part of January was because of unusually high temperatures. So this is the temperature anomalies in degrees Fahrenheit relative to average since January 22nd. You can see over most of the region, temperatures were running 2 to 4 degrees warmer than average since this period. This was coming on the heels of what was a very cold period in the beginning to the middle of January. And if we look at the same data but expressed as a percentile, we see that most of the region was well above average, and much of the region was in the 90th percentile. So among the few warmest years on record for this period. Okay, shifting gears a bit, this map shows current stream flows. So this is the 7-day average ending last week. Most of the region stream flows are right around average, with a few exceptions. The Klamath and Puget Sound basins are running below average. There are also some sites or some stations along the Snake River that are well below average, likely due to reservoir management. If we take a longer view here, this is the 28-day average stream flow compared to historical. So this is monthly average ending February 21st. We see much of the region have stream flows well above average, especially in the Central Cascades of Oregon, much of northeastern Oregon and eastern Washington as well. This was not due to unusually high precipitation over this period, but rather because of those warm temperatures that I just showed, resulting in above average snow melt, especially at the lower elevation sites. So it's good that the stream flows are strong, but this is not for the reason that you would want. This is due to accelerated melt out during what we would want to be the accumulation season. The good news is that there's lots of snow expected this week. So this is the forecast for snow accumulation according to the high resolution model that's run at the University of Washington. This was initialized yesterday, and this is the 7-day total. So over much of the Cascades, we're expecting snowpack accumulation of 3 to 4 feet or even a bit more in some places, and lots of accumulation in the Rockies as well. So that is good. The bad news is that we're still in El Nino, and the longer range forecasts, as Aaron will probably discuss, call for likely warm conditions and slightly more than likely conditions of, slightly more likely than not that it will also be below average precipitation over the next few months. So this suggests an elevated risk of snow drought heading into the summer. Okay, so just to summarize, drought conditions in the Northwest haven't changed much since December. Roughly 10% of the region is in severe drought, 26% of the region, or 16% of the region is in D1 drought. Precipitation and snowpack are close to normal in the southern part of the Pacific Northwest, much of Oregon and southern Idaho, but below normal in the north. And warm temperatures in recent weeks have contributed to the large snow deficits at lower elevation sites, especially west of the Cascade Crest. The next week looks great. We're likely to see an increase in snowpack across the region due to a series of storms impacting the region. But longer term, it's still more likely than not that conditions will be relatively warm and dry. This suggests an elevated risk of drought, especially snow drought, to begin the summer. So with that, I'll turn it over to Aaron.
Great, thank you so much. I'm going to transition the presentation to Aaron. And as he's bringing up his slides and digging a bit deeper into the outlook, I was just we had two comments. One that someone said they're seeing the lower elevation SWE in the Willamette as well. And then We had a question about the forecasted snow, but I think between the end of your presentation and what Aaron's going to dig a little bit deeper into, that question will be answered. So I'll turn it over to you, Aaron.
All right, thanks, Britt. Can you all see my screen?
We can.
Okay, cool. All right, thanks for having me. My name is Aaron Peters. I am the Western Region Hydrology Program Manager for the National Weather Service. And as they mentioned, I'm going to go into a little bit more detail about some of the outlooks that we are looking at for the next several months. First off, I just wanted to show, this ties in perfectly with what Nick was showing as far as a shorter term kind of positive impact that we're expecting over the next 10 days or so. These are two graphics from the Northwest River Forecast Center in Portland showing 10-day quantitative precipitation and or QPF, and then that QPF percent of climatology. So as you can see, excuse me, on the left plot is the total water equivalent that we're expecting over the next 10 days or so across the basin, and that includes the entire Pacific Northwest Northwest River Forecast Center basin. And then on the right is the percent of climatology. So we're seeing some pretty significant numbers as compared to climatology, like greater than 175% of average there across large swaths of the area. And a particular note that is encouraging is those areas in western Montana and northern Idaho that are already suffering from D2 drought or a little lower. Those areas are going to see some significant precip, which will certainly do nothing but benefit that drought situation. So looking at the, let's see, next slide. So Nick showed the 3-month, which is on my next slide, but it's really kind of a rinse and repeat of from a monthly outlook out to the 3-month outlook. This is for March. It was issued February 14th, so 15th, so about 10 days ago. And shows a similar kind of signal that we've seen really since last fall, when this El Nino was forecast to materialize. So sort of a below average precipitation signal and a above average temperature signal. So of course, we should note that these shading, so the shading for the precipitation, you see that the darkest shade there is 40 to 50% chance of below normal. So that means that we're sort of leaning below, not necessarily all that, strong of a signal, because of course, if there's a 40% chance of being below normal, there's a 60% chance of being near or above normal. So that is the kind of trend that we're leaning towards March, but we were leaning that way in February as well, and we've seen some pretty decent precipitation in February. So it'll be interesting to kind of see how March plays out, because March is often, a really good time of accumulation for snowpack in a lot of the higher elevations. So those areas that are in the maybe normal to slightly above normal might benefit. But of course, the temperatures may just melt all that snow out. So we'll see. But looking at the 3-month, I'm not going to focus on this too much because Nick showed it, but similar kind of trend, right? And again, this is something we've kind of seen over the last several months kind of persist. Looking at the Northwest River Forecast Center 120-day streamflow forecast. So this is a water supply forecast for these points, and they're color coded, of course. Anything that's kind of green into blue or above is normal to above normal, and then anything yellow to those darker shades of orange and red are below normal forecast for the next 4 months. And as you can see, it's sort of a mixed bag across the area. So those areas in northern Idaho and western Montana that are suffering from pretty good snow drought, they are seeing those below normal streamflow forecasts pretty clearly. And then eastern Washington, similar kind of story, but as you move into the Cascades in northern or western Washington, the forecasts improved quite a bit. And then, southern Idaho, that Snake River, Boise River area is looking pretty decent down there as well. So Again, these forecasts really kind of come into focus even more when we sort of end our snow accumulation season. But this is kind of the picture given the current conditions that we're seeing. Looking at the seasonal drought outlook. So this is a Climate Prediction Center product that takes into account the current drought coverage across the area, and then looks at the Climate Prediction Center's forecast for seasonal temperature and precipitation, kind of tries to give us an idea of what we might expect. So the main thing we can sort of take from this is that drought that we're seeing existing currently in northern Idaho and western Montana is probably going to persist. That's in that kind of brown color, which we may see some improvement, but this is really through the middle of February, valid from the middle of February through the end of May. So, and that is, pretty reflective of the fact that we are anticipating staying in this El Nino pattern that we've been in all winter, at least through the end of May. So, and that does tend to, not favor a bunch of drought improvement. So, the areas that you can see in yellow in Washington and Oregon are where drought development may occur. And of course, there's not a huge area there, but with that drier than normal and warmer than normal signal that we saw in the climate predictions and our outlooks, that's probably where those are coming from. So some possible positive news is that we are under a La Nina advisory. So current, if you can see that, I don't know if you can see my mouse, but the black dot on the left of this plot has us current conditions, and we're squarely, in the El Nino territory for sea surface temperatures. But almost all models and ensemble members are showing a trend toward moving into a La Nina this summer. So we're looking at like a 79% chance of going back to ENSO neutral by late spring, so April to June, and then 55% chance of La Nina developing from June through August. So that usually is a positive signal for water supply. Of course, it doesn't help us this year, but may help us next year, depending on how strong it is and what plays out. This is just another graphic showing sort of the same thing, but gives you kind of like a more of a timeline. So again, February, March, and April is where we're sort of at now for this this model-based probabilistic forecast. Of course, we're at 100% chance of El Nino because that's where we're at. And then, but really by April, we're looking at a 70% chance of April, May, June, July of being in neutral, and then pretty good chances October, September, October timeframe, a 70% chance of La Nina. So this forecast was actually produced in the middle of February as well. I think it was the 15th or so. The official CPC outlook was done in the beginning of February. It shows a similar pattern, but this is actually showing a little bit stronger with a 2-week update. So that's looking fairly likely. And for those of you that have been keeping track, this will be if this does end up in a La Nina for this winter, it'll be our 4th La Nina in 5 years. So we had 3 in a row, and then we went to El Nino for this current winter, and then possibly back into La Nina for next winter. So kind of remarkable. All right, looking at just a few key points. The 10-day precipitation forecast for much of the Pacific Northwest is positive, a lot higher than normal. Will certainly do nothing but help the water supply situation in the area. And then spring 24 is really leaning warmer and drier than normal. Again, it's sort of that pattern we've seen for forecast-wise over the last 6 months. Of course, we will have events in there that help the situation, but maybe averaging out, we're not gonna be higher than normal for precip. The stream flow forecast across the region, again, kind of range from well above to slightly below normal. So really kind of depends on a lot of this precipitation or drought has been somewhat localized in the region. So just depending on where you're at is where your stream flow forecasts are looking right now. Northern Idaho and western Montana will probably see their drought conditions that they're seeing now persist through the spring. Certainly hope that by May, June, July timeframe, spring rains will improve that. I guess that's just something we'll have to keep an eye on. And then, of course, the transition from current El Nino conditions to La Nina is expected, and that's going to be, hopefully by late summer of 2024, and likely last through the winter if they do develop. And of course, the effects of La Nina are most pronounced during the cool season for this part of the country. So hopefully some positive news there. And that is all I had. Feel free to email me if you have any questions. Thanks.
Great, thank you, Aaron. There's no questions right now, so I'm going to go ahead and share my screen and invite Ben to present.
Cool. Can you hear me okay?
Yeah, and give me a second, I'm pulling this up.
Yeah, I'll just start while you do that.
Oh, hold on. There we go.
Oh, perfect. Yeah, hi everybody. My name's Ben Roberts-Farrell. I did most of this work, all this work, while at Oregon State University. I've since moved on and worked for a contractor for the USGS on the Landsat Next project. I work out of the Arrows facility in South Dakota, although I work remotely. So today I'm going to talk about snow drought in the Pacific Northwest and something about the role of data selection and something a little bit about processing data. I'll just quickly acknowledge Mark Rowley and Robert Kennedy, who also were co-authors on this project and made a great contribution to the work. Next slide, please. So I think we can just skim over this. Everybody's pretty familiar with the Pacific Northwest. We've just talked about how important snow is to the overall water context in the Northwest, how snow is changing, and is highly susceptible to, especially in the Cascades of Oregon and Washington, to slight changes in temperature as it tends to exist close to 0 degrees Celsius. In the figure there on the right, I'm just showing temperature, precipitation, snow water equivalent, and then a digital elevation model. And I'll quickly mention that this work is hopefully in the last round of reviews to be published in Water Resources Research. So just in the context of you can't get all of these things yet, but ideally in the fairly near future. We can go to the next slide. So this research kind of looked at a few things related to snow drought. The first question was sort of how often, when, and where snow drought has occurred. I'm just going to focus on those first two, kind of how often and when snow drought occurred in the interest of time. Secondly, we kind of looked at a couple of different data sets and how the identification of snow drought varied depending on the data set type that was selected. And then finally, we looked at identifying snow drought using a common remote sensing product from MODIS, so an optical remote sensing product without using additional climate data. I've only underlined these here to say that this is remote sensing from a satellite in a visible near infrared or shortwave infrared, not a radar instrument. And then climate data here, I just mean like temperature and precipitation primarily. So all it's measuring is like snow covered area. We can go to the next slide. So the definitions that we used were from a paper from 2019 to differentiate dry, warm, and warm-dry snow droughts. I know there's a variety of different definitions out there. We mostly did that so that we could make these differentiations between these different types of snow drought. The definitions are based on a comparison against a 30-year mean. And then for the purposes of our research, we split the winter into these 2-month periods. I know obviously there's a lot of different ways you could go about doing that, but we refer to them as these early, mid, and late periods, mostly so that we could have a sort of defined period of time that we could compare between data sets and different places, so that we had this unit of measurement and comparison. We can go to the next slide. So the definition of snow droughts was primarily based on these three qualifiers: precipitation, temperature, and snow water equivalent, which has already been mentioned. So I won't go into that too much, but for everything but the optical remote sensing product, those are the predictors that we're using to qualify snow drought. We can move to the next slide. The spatial units are defined by the hydrologic unit codes. Most of this research focuses on Huc 8 basins. We used a gridded SWE product from the University of Arizona. We used a lot of data from the SNOWTEL network. We combined the University of Arizona SWE product with the PRISM data to give us temperature and precipitation. Going forward, I just kind of refer to that as UA SWE as this combined product, just for brevity. And then, like I mentioned, the remote sensing product comes from the MODIS instrument off of the Terra satellite, and that is a very widely used optically remote sensing snow product. So I'll come back to that at the end. We can go to the next slide. All right, so I'm going to give kind of an overview of some of the results, just hitting a few high points as there's kind of a lot of information in these plots. But this is aggregated snow droughts for Huc 8 basins for the whole study period, not considering specific snow drought types. Generally, what we found here is that between the UA SWE combined product and the SNOWTEL point product, that the annual number of droughts was, the mean number of droughts was pretty similar, although there was some disagreement in the minimum and maximum years. So for example, SNOWTEL identified the 2015 water year as the maximum number of snow droughts, which if you have been in the Pacific Northwest for some time, you'll know that that was an exceptionally low snow year. That was, I think, the second highest in the UA SWE product, and then there was some dissonance in the lowest year between the two products as well. For both data sets, we observed the largest increase in net number of snow droughts from the first decade, that would be 1990 to 2000, to the second decade, 2000 to 2010. We can go to the next slide. So there's a lot of information here, but I'm just going to sort of draw your attention to the upper left and lower right plots that are highlighted in red. Of these sort of disaggregated snow drought types on the y-axis, or sorry, on the x-axis, and the periods of the winter on the y-axis, the only sort of combinations of those that we found statistically significant trend results for were dry snow drought in the early winter for SNOWTEL data, which decreased, and warm dry snow droughts for SNOWTEL data in the late winter, which increased. And we did not find statistically significant results in the other periods. I highlight this mostly to show that the results for these individual pairings are fairly different across the winter and across the snow drought types and across the data sets. So making this disaggregation shows, yeah, quite a bit of variability across those factors. We can go to the next slide. So if we dig into some of the predictor variables that I mentioned, that being SWE, temperature, and precipitation, this is just all the raw data that went into these classifications compared at a SNOWTEL to the University of Arizona SWE dataset grid cell that is coincident with the SNOWTEL site. This doesn't consider anything with drought conditions, it's just all the underlying data. That basic correlation between the two data sets is generally quite good. That's not terribly surprising. There's been a lot of analysis on these types of data sets. So at the point to grid cell, that comparison is pretty good. We can go to the next slide. However, if we disaggregate that again and we look at how that breaks down over the winter periods and under different drought conditions, we find that there's a huge amount of variability. And again, this is also aggregated to Huck 8. So in this case, I won't try to sort of assign how these correlations change, but there's a certain amount of uncertainty that's introduced by the aggregation, as well as how this sort of varies throughout the year and across snow drought types. So if we just consider, for example, the dry snow droughts in the early part of the winter in the upper left subplot, the correlation is relatively good. But if we compare that to, say, warm snow droughts in the late winter, that would be subplot H. The correlation really breaks down, and we're seeing quite different results from the UA3 data set versus the SNOWTEL data set. We can go to the next slide. So to the last point that I introduced at the beginning, this is the remote sensing data. What we found here was that the only statistically significant results between the groups was that we could identify snow drought as being different in the warm, dry condition from the other groups in the midwinter and in the late winter, but we could not identify a statistically significant difference in the other groups in the midwinter or the late winter, and we found no statistically significant results in the early winter, meaning that this data set was not identifying a difference between any of those drought conditions and no drought conditions in the early part of the winter. So we can move to the next slide. So this is just, some conclusions, takeaways. So generally, snow droughts have increased, but not in a linear fashion. And the sort of increase has varied quite widely across time and the type of snow drought, locations, which I didn't talk about here, as well as the data set that you're using to classify. In that point to grid cell comparison, the predictor variables look pretty similar, and I will note that temperature and precipitation followed a pretty similar trend to SWE. However, that kind of breaks down or changes when you look at snow drought conditions throughout the year. And then on the optical remote sensing side, it is a product that may not work well for identifying snow drought in the early winter, and even in the mid and late winter may struggle to identify all but the most sort of quote unquote severe snow drought conditions. But that I think is an area of future study, as that's such a widely used product. And with that, I will wrap up and stop with my time. Thanks.
Thank you so much. I am going to go ahead and move to David's presentation, and then we'll circle back on questions. So David, I'm going to go ahead and give you permission now to share your screen.
Okay, Britt, did that work?
Yeah, but if you put it in presenter mode, it looks like it should work.
That's what I've got on my screen. Do you not have that?
No, we're still seeing this, the small slides in your notes.
That?
It's still not changing.
No.
I can take it back and give it to you again and see if that.
Yeah, I'm not showing in presenter mode. I'm just clicking on play from start.
Yeah, we're still just seeing the notes and the.
Correct. Yeah. So I'm not quite sure with this particular platform that we're using how to make that any different.
You're welcome, just in the interest of time, to make the slide as large as you can and proceed.
Yeah, weird. No idea.
Sorry about that.
Yeah. Is that going to work all right?
Yeah, can you move the window over a little bit? We're not seeing the whole slide right now. Just the,
Can I just, if I close this, is it going to kick me out of the call or not?
I don't know.
Is that out of the way well enough?
So what we're seeing your slide,
Yep.
but it's cutting off the far left-hand side. So if you can just move the whole PowerPoint or whatever window over just a little bit and see if we can see the entire slide.
I'm not sure I can do that.
Okay, let me take back presenter control and pass
Yep.
it to you and see if that maybe.
Yeah, because this worked earlier for us.
Yeah, hold on. Okay. Okay, it should be coming back to you. See if that works. There, that's better.
Is that going to work all right?
That'll work fine. Thank you.
Okay. Yeah, sure. Not sure what happened there, but okay. In any event, oh, actually, I'm not quite sure. There we go. Fine. Great. Sorry about all that. Yeah, so, I think a lot about, the different ways of kind of getting snow measurements. And this is, of course, my favorite. This is field work in Alaska, but it's, slow and expensive. We are very lucky in the Western US to have all of these great sites as well. So the SNOTEL and the snow course networks are fantastic. But again, they're just point measurements with lots of gaps in between. Modeled products like SNODAS is fantastic. Gives us the coverage over the entire country, which is terrific. At a daily time scale, 1 kilometer grid. So there's an awful lot to like about that as well. But then there's some things to not like about that as well. So this is a picture of what SNODAS says is going on a particular day over the Tetons, and just huge disagreement in terms of what that model product sort of shows us in terms of snow cover versus what we see from the aerial imagery on that day. So, if I had to sort of think of like the perfect snow measuring program, it would be this. You can think of it in terms of how often do we measure, at what spatial resolution do we have information, and what spatial coverage. So the perfect thing would be sort of over at the right. And of course, that thing does not yet exist. And so we have to make decisions about how we're going to get the information that we want. So the first few minutes of my talk today here is just briefly about the Community Snow Observations Project, which is a community science project based on recruiting participants to collect snow depth information. And we've targeted various audiences, both professionals, recreationists, educational programs as well. And the way that this program works, it's very simple. This is sort of it in a nutshell. So we do all the modeling kind of in the upper portion of this diagram, and where the participants come in is in the orange box there. So their observations are assimilated into the modeling that we do, and are essentially always nudging our model estimates back towards ground truth. The way to participate is really straightforward. And you pick the measuring device of your choosing. Can simply be a meter stick, can be a ruler if you got really shallow snow, can be an avalanche probe if you have that in your backcountry kit. And then these are all measurements made in the field, so they're geotagged and also time-stamped with people's phones. And we actually use what's the SnowScope app from a company called Propagation Labs, which is extremely easy to use. And does it work? In this particular case, what we're looking at is we have the red line is SNOTEL at a particular. This is in Utah at a particular location for a particular water year. The sort of dark blue line is our best calibrated model run for that area with no assimilation. And then when we start getting participant snow depth information, you can see that it corrects our simulations very well, which is great. And so it's been a super successful program. We also serve all this information up daily, real time, so you can go and interact with and explore and download all of these data, if you will. This sort of shows you in the Western United States, we have about 13 domains, and we continue to roll out new domains where we do this modeling, kind of based on where we see participation. So when we start seeing lots of observations come in, we sort of divert some of our modeling resources. in that direction. And this is the kind of information that you can get. So this is actually the Mount Hood area on a given day. The nice thing about sort of showing this diagram is kind of the highlighting the importance of the high resolution. So the Snowdass product on the right is very grainy, and it doesn't really pick up the landscape of Mount Hood very well. Whereas we model, I think, Hood at 30 or 50 meters spatial resolution. So that's kind of the quick tour on the Community Snow Observations project. The other thing I wanted to briefly talk about today is sort of ways of kind of quantifying sort of our snow resources. And so this is a figure that many people will be familiar with from Moach study back in 2015 or 2018. And this is based off of snow courses. So they looked at the monthly measurements from snow course data and did a lot of great sort of analysis of changes observed at those sites. This is actually, and change is important, of course, over multi-decadal scales, but even on shorter scales. So this is the Hog Pass Snowtell site, sort of just east of Corvallis, up in the mountains. And the kind of dramatic drop-off, sort of post 2010, is really significant in terms of looking at the maximum observed snow water equivalent. And this is also from Oregon. This is a Snowtell site in the northwest part of the state, up in the Coast Range. And the reason I like showing this is that it really sort of shows that snowpack can be unbelievably variable from year to year and can sort of defy what we think of as a typical snowpack in a high mountain environment where we have an obvious accumulation phase and then a melt phase. So this is a region really characterized by ephemeral snowpacks. And it's very difficult to look at this and be like, well, we should be sort of quantifying our snow on April 1st of the year or March 1st. We're not sure. Every year is so dramatically different there. And so that was kind of the point of this study, is we started thinking about like what your classic snowpack might look like and how it might change sort of from the past to today or from today into the future. The snowpack could shrink, it could move forward earlier in time, it could become more ephemeral in terms of repeated accumulation and ablation stages. And we were really interested in like, can we quantify this in a better way than just picking a maximum snowpack value or an April 1st snowpack value? And so what we basically did is we're like, well, let's just actually integrate the area under the curve, because that sort of tells us the complete seasonal story of how much snow did we have, when did we have it, and for how long did we have it. So it's that integral, which is what we've been referring to as the snow water storage. And these are some results from a paper that we just published last week on this in Hess. And on the left, it's raw units. On the right, it's percentage. And the larger dots are statistically significant changes at these Snowtell sites. And on the right, if you're looking at the right side in terms of percentages, anything yellow, orange, red is bad, and anything sort of bluish to greenish is okay. And so while there are, of course, a few locations, sort of more continental snowpacks, where there are increases, overwhelmingly decreases in snow water storage. And it's nice because since we're not just looking at like April 1st snow, we can look at the snow water storage in a given month. And so this is basically all of those sites from the previous page. And when we break it down by month, we can see in what months we're having the strongest, most rapid declines in snow water storage in that month. In this figure, what we're trying to do is to kind of highlight the difference between the snow water storage metric versus something like April 1st. And so here what we're showing you is we're only showing stations where there are disagreements between the trends, right? So if we have stations where the snow water storage in April 1st SWE are changing in the same way, we don't show those here. So we're only showing ones where there's divergence. And what we can see is when we look at just those stations, we can see that there are a lot more stations where there's a significant decrease in the snow water storage, but actually the April 1st snowpack looks like it's kind of holding steady, right? And the final thing is that this simple idea of just kind of integrating under the SWE curve is something that can be applied at stations, but can also be applied to anything you want. And so this is the University of Arizona SWE product, and there are many other products where you can get this sort of gridded snow information as well. And so you can sort of perform these calculations on a gridded basis as well. And so this is showing the percent change over the 1980 to 2020 timeframe for the annual snow water storage. And again, similar patterns in terms of large decreases in the western U.S. and the upper Midwest and so forth, actually showing some increases. So only two quick parting thoughts. Number one, casual data from the public is amazing. CocoRa's project is amazing. We've been able to do great things with the data that we get from the public participating in our project. And then second parting thought is just be thinking about more nuanced metrics of how we actually quantify our snow in the ways that we quantify it. So thanks very much.
Great, thank you, David. There are a few questions in the chat box, so I will start asking those questions, and then I will also post all of our presenter emails. So if you have any questions, you can email them directly. Our first question is perhaps for Nick or perhaps Aaron. Why is snowpack west of the Cascade Crest so low? I've noticed a lot of reservoirs are still low as well. Do we know why?
Yeah, I can take a stab at that. I mean, these are locations, actually, I think Ben sort of made this point. These are, tend to be stations where snow falls up pretty close to the freezing point, and so they're, pretty vulnerable to increases in temperature. So over the last month, I showed temperatures across the region have been, anywhere from 2 to 4 degrees above average. If you look at the overnight lows, the anomalies have been even higher. So these are, stations where, if it were 4 degrees cooler, we might have seen precipitation falling as snow instead of rain. But the fact that it has been as warm as it has been, especially in the last month, means that a lot of the precipitation those sites have received has been rain rather than snow.
Great, thank you. I think this next question is for Ben. For the snow drought study, what was the study region you used?
Yeah, we confined it to Washington, Oregon, and Idaho. We didn't extend it to the Columbia River Basin, mostly because PRISM is a CONUS product. So we didn't extend our basins into Canada. So we just cut it off at that for practical reasons, mostly.
Great, thank you. And our final question, I'm not sure who may want to take this, or we can follow up with the person asking, is how do SWE predictors and SNOWTEL sites compare with reported impacts? And I'm not sure, maybe I can follow up with the person asking the question just to try to understand that question a bit better. And then we'll try to reach out with an answer. So with that, I think that's all the questions I'm seeing. So thank you so much to all of our presenters today. And if you'll mark your calendar, our next webinar will be on April 22nd, and we look forward to seeing you then. As always, if you have any general questions or want to get in touch with the speaker, you're also welcome to email me. So thank you for taking part in today's webinar, and we'll see you in April.